All right, gentlemen, writing algebraic expressions is a huge challenge for secondary 2 students, but it's a challenge you can meet. It's a challenge you can handle, and you'll see that there's some techniques that can make it a lot easier, and we're going to look at one today. The technique we're going to look at today is called the CSI technique. The CSI technique. Now, why is it called the CSI technique? Well, because CSI is a show where they go to the scene of the crime and they try and figure out what happened based on what they see there. So that's kind of what we're going to apply to algebra here. You'll see that we'll apply these steps and they'll become a lot more easy to understand if we actually start applying them with an example. We're going to use a made-up number, then we're going to do the math with that made-up number, then we're going to figure out what we did CSI style, and then we're going to use that to figure out how to write an algebraic expression. So an algebraic expression, we've already seen these for a while. An algebraic expression is just a combination of usually numbers and variables, sometimes just variables, but usually coefficients, sometimes constants as well. And it's an abstraction. It's a not one concrete value, but an expression that could have multiple values. Now, if you're looking at this one here, this example is asking us to write an algebraic expression for the amount of money our friend Robert makes if he works 35 hours. Now, the problem is that he works for X dollars an hour. That's his salary. And that's when we're writing algebraic expressions. That's what makes this a little more challenging. If it just said, well, Robert makes $2 an hour, well, that's not great for poor old Robert, and he seems to be exploited by his employer. But if we knew that he made $2 an hour, then how much money does he work if he works 35 hours? Most of us would say, well, I'm just going to multiply 35 times 2 to get $70. That's how much he makes if he works 35 hours at this horrific wage of $2 an hour. Now, if that's easy, then we should exploit the fact that that's easy, even if it might seem to us that dealing with variables could be a bit more of a challenge. So here's how you do it. You say to yourself, I just made up a random value for how much he makes an hour. I turned that algebra into just numbers because I might feel a little more comfortable with just numbers. And once I knew it was just numbers, it was easy for me to figure out what this amount would be. I replaced x with 2, and suddenly this problem became easy. And that's what this technique relies on. That's when you see here when it says step 1, use a made-up number. That number 2 that we made up here as the value he makes an hour, we replace the variable with some made-up number. I could have used 10. I could have used 100 if I wanted to make it so that Robert makes a better wage. But whatever value I use, I then do the problem as if that's the actual amount, and then I figure out what I did. So what I did was, once I knew it was $2 an hour, I instinctively multiplied it by 35 to get 70. So what I do now is I go back and I replace my made up number, which was 2, with the variable. The variable is x. So I go and I say, instead of 35 times 2, I would do 35 times x, because 2 was just the number I made up to replace x. Now that I've replaced 2 back with x, this is actually the answer to my question. How much money does he earn if he works 35 hours at x dollars an hour? He earns 35 times x dollars. That's my answer. That's my algebraic expression. All right, the technique isn't too complicated. We saw it there. Let's see it on another one. If each side of a pentagon measures x centimeters, what is the perimeter? Well, if I'm looking at this and I'm saying, well, a pentagon, I can, I don't know about this X stuff. I'd much rather if it were just number, then let me turn into that. Let's take my pentagon. Let's pretend that each side of the pentagon measures not X centimeters, but 100 centimeters. If each side of a pentagon measures 100 centimeters, well, I guess you'd have to know how many sides a pentagon has. Pentagon looks kind of like this. It's got 5 sides. Penta is just Greek for 5. That part of the word means 5. So if I've got 5 sides and each of them is 100 centimeters, then I can do 5 times 100 to figure out my total perimeter, which is going to be 500 centimeters. Now, an important part of this technique, and we saw in the last one, you see it here as well. So if you go back and you look here, it says write it out when you do the math, right? It's important that when I replaced my variable here with a number, I then wrote out the math I was doing, 5 times 100. Because it's once you've written it out that you can see, all right, this 100 showing up in my written out math here, that's my made up number. And that means that if I just, the way I've written it out, go back and replace that with x, I'll have my answer. And this is my answer. 5 times x is my perimeter if each side is x centimeters. 5x centimeters is my perimeter, just like that. Okay, let's see it again. This one's more challenging. If one of the acute angles of a right triangle, all right, let's get some tools here to draw a right triangle. Got a right triangle here, and like any triangle that we're going to deal with this year, it's going to have 3 angles to it, and one of those angles is going to have to be 90 degrees because that's what makes it a right triangle. It says one of the acute angles, I got 2 of them. This one here is less than 90, this one here is less than 90. If one of these measures a degrees, what is the measure of the other one? Well, important for this to know is you've got 180 degrees total in a triangle. That's something that if you don't know that, you can't really do this problem. But if I know this angle is a degrees, let me say, well, this would be easier if we're less algebra-y. Let me replace that with some number, like I could say, I don't know, 10 degrees. Okay, 10 is often a great number to just throw into these. So if this is 90 degrees here, and this is 10 degrees here, and I'm trying to find this angle here, well, I know all 3 of them, like the 90 plus the 10 plus this guy are going to add up to 180, right? So this 90 degrees here and this 10 degrees here total to 100. That means 180 minus 100 is going to give me my missing angle, right? In this case, 80 degrees. So I added my 90 degrees and my 80 degrees together, and then I took them away from 180. This, let's see here. I didn't write this out very well, but really what I did was 180 minus 90 plus 10 to get my answer. And remember, 10 was just my made up number. So if I go back in and I replace that 10 with my variable, I'll have my expression here. It wasn't 10 degrees, 10 was just standing in for a degrees. So my expression is this, 180 minus 90 plus a. I think I'm going to simplify this, right? I'm going to distribute that negative to get 180 minus 90 minus a, and that becomes 90 minus a degrees.